In computer science, evolutionary computation is a subfield of artificial intelligence that can be defined by the type of algorithms it is concerned with. These algorithms, called evolutionary algorithms, are based on adopting Darwinian principles, hence the name. Technically they belong to the family of trial-and-error problem solvers and can be considered global optimization methods with a meta-heuristic or stochastic optimization character, distinguished by the use of a population of candidate solutions. They are mostly applied for black box problems, often in the context of expensive optimization. Evolutionary computation uses iterative progress, such as growth or development in a population. This population is then selected in a guided random search using parallel processing to achieve the desired end. Such processes are often inspired by biological mechanisms of evolution. As evolution can produce highly optimized processes and networks, it has many applications in computer science. History. The use of Darwinian principles for automated problem-solving originated in the 1950s. It was not until the 1960s that three distinct interpretations of this idea started to be developed in three different places. Evolutionary programming was introduced by Lawrence J. Fogel in the US, while John Henry Holland called his method a genetic algorithm. In Germany, Ingo Reichenberg and Hans-Paul Schwefel introduced evolution strategies. These areas developed separately for about 15 years. From the early 90s on, they are unified as different representatives of one technology, called evolutionary computing. Also in the early 90s, a fourth stream following the general ideas had emerged, genetic programming. Since the 1990s, nature-inspired algorithms are becoming an increasingly significant part of evolutionary computation. These terminologies denote the field of evolutionary computing and consider evolutionary programming, evolution strategies, genetic algorithms, and genetic programming as sub-areas. Simulations of evolution using evolutionary algorithms and artificial life started with the work of Niels All Baricelli in the 1960s. And was extended by Alex Fraser, who published a series of papers on simulation of artificial selection. Artificial evolution became a widely recognized optimization method as a result of the work of Ingo Reichenberg in the 1960s and early 1970s, who used evolution strategies to solve complex engineering problems. Genetic algorithms in particular became popular through the writing of John Holland. As academic interest grew, dramatic increases in the power of computers allowed practical applications, including the automatic evolution of computer programs. Evolutionary algorithms are now used to solve multidimensional problems more efficiently than software produced by human designers, and also to optimize the design of systems. Techniques. Evolutionary computing techniques mostly involve meta-heuristic optimization algorithms. Broadly speaking, the field includes ant colony optimization, artificial bee colony algorithm, artificial immune systems, artificial life, Bayes algorithm, cultural algorithms, differential evolution, dual-phase evolution, evolutionary algorithms, evolutionary programming, evolution strategy, gene expression programming, genetic algorithm, genetic programming, harmony search, learnable evolution model, learning classifier systems, particle swarm optimization, self-organization such as self-organizing maps, competitive learning, swarm intelligence, evolutionary algorithms. Evolutionary algorithms form a subset of evolutionary computation in that they generally only involve techniques implementing mechanisms inspired by biological evolution such as reproduction, mutation, recombination, natural selection and survival of the fittest. Candidate solutions to the optimization problem play the role of individuals in a population, and the cost function determines the environment within which the solutions live. Evolution of the population then takes place after the repeated application of the above operators. In this process, there are two main forces that form the basis of evolutionary systems. Recombination and mutation create the necessary diversity and thereby facilitate novelty, while selection acts as a force increasing quality. Many aspects of such an evolutionary process are stochastic. Changed pieces of information due to recombination and mutation are randomly chosen. On the other hand, selection operators can be either deterministic or stochastic. In the latter case, individuals with a higher fitness have a higher chance to be selected than individuals with a lower fitness. But typically even the weak individuals have a chance to become a parent or to survive. Some evolutionary computation practitioners. The list of active researchers is naturally changing over time. A good network analysis of the community has been published in Thomas Beck, Wolfgang Banzhaf, Kalyan Moideb, Kenneth A. de Jong, Gus Iban, Peter J. Fleming, Stephanie Forrest, David E. Goldberg, Emma Hart, John Henry Holland, John Koza, Zbigniew Michalewicz, Peter Norden, Ricardo Poli, Ingo Reichenberg, Mark Schernauer, Hans-Paul Schweffel, Jim Smith, Xin Yao. Bibliography. Th. Back DB. Fogel, M.Z. Michalewicz, Handbook of Evolutionary Computation, 1997, ISBN 0750303921. Th. Back in H.P. Schweffel. An Overview of Evolutionary Algorithms for Parameter Optimization. Evolutionary Computation, 1-1-23, 1993. W. Banzhaf, Norden, R.E., Keller, and F.D. Franken. Genetic Programming, An Introduction. Morgan Kaufman, 1998. S. Cagnano, al. Real-World Applications of Evolutionary Computing. Springer Verlag Lecture Notes in Computer Science, Berlin, 2000. R. Keown, Th. Wise. Michalewicz, Variants of Evolutionary Algorithms for Real-World Applications, Springer, 2012, ISBN 3642234232, K.A. De Jong, Evolutionary Computation, A Unified Approach, MIT Press, Cambridge, Massachusetts, 2006. A.E. Iban and M. Schernauer, Evolutionary Computing, Information Processing Letters, 82, 1-6, 2002. A.E. Iban and J.E. Smith, Introduction to Evolutionary Computing, Springer, 1st edition, 2003, ISBN 3-540-40184-9. D.B. Fogel, Evolutionary Computation. Toward a New Philosophy of Machine Intelligence. IEEE Press, Piscataway, N.J., 1995. L.J. Fogel, J. Owens, and M. J. Walsh. Artificial Intelligence Through Simulated Evolution. New York, John Wiley, 1966. D. Goldberg. Genetic Algorithms in Search, Optimization and Machine Learning. Addison Wesley, 1989. J. H. Holland. Adaptation in Natural and Artificial Systems. University of Michigan Press, Ann Arbor, 1975. P. Hingston, Barone, M.Z. Michalewicz, Design by Evolution, Natural Computing Series, 2008. Springer, ISBN 3540741,097. J.R. Koza, Genetic Programming. On the Programming of Computers by Means of Natural Evolution. MIT Press, Massachusetts, 1992. F.J. Lobo, C.F. Lima, Michalevich, Parameter Setting in Evolutionary Algorithms, Springer, 2010, ISBN 3642088929. Z. Michalevich, Genetic Algorithms plus Data Structures, Evolution Programs, 1996. Springer, ISBN 3540606769. Z. Michalevich and D.B. Fogel, How to Solve It. Modern Heuristics, Springer, 2004, ISBN 978-3-540-22494-5. I. Reichenberg, Evolution Strategie, Optimierung technischer System nach Prinzipien des biologischen Evolution. From Ann Hosbeck Verlag, Stuttgart, 1973. H.P. Schweffel, Numerical Optimization of Computer Models. John Wiley & Sons, New York, 1981. 1995 2nd edition. D. Simon, Evolutionary Optimization Algorithms. Wiley, 2013.